I'm Tadashi Wadayama. I'm working with the Nagoya Institute of Technology. Today, I'd like to talk about the estimation problem of mutual information by using the score function. So our target channel is very simple. You can see that equation 1 is our target channel. Random variable x represents the input, which can take arbitrary prior probability distribution. And now you can see there is a function f. F is a deterministic nonlinear function, which is called front-end function in this talk. And the next one, eta, is the vector which controls the shape of f. So f can be set as a parameterized function. So for example, in the case of neural network, the weight and bias vector correspond to eta. And zt represents the Gaussian noise. T represents the variance of the noise. So our goal of this study is to estimate efficiently and accurately estimate the mutual information I, X, Y. So because this mutual information is the fundamental measure for measuring the quality of the channel, so it is very important. So there are so many practical situations we can encounter the nonlinear front-end function like this. For example, in the case of nonlinear RF amplifier, we have some kind of saturation or clipping in the amplifier. DAC, ADC introduces, of course, nonlinearity. And in the case of optical communication, there are many sources of nonlinearity. And also, nowadays, you know, in the encoder side, we often use the semantic neural net encoder. So in that case, F can be regarded as the neural network, okay? So this is an example of input-output model of the nonlinear lapped model for RF amp. So horizontal axis represents input and vertical axis denotes output. So you can see the strong nonlinearity. There is a strong saturation around if the input is large. So this figure shows the case of the optical fiber communications. It is well known that the wave propagation in the optical fiber is dominated by nonlinear Schrödinger equation written in 4. So you see there is the, on the right-hand side, there is a term including U, absolute value of U squared. This introduces the nonlinearity into the wave propagation. Okay, so what's the benefit of mutual information estimation? We can say that mutual information can be regarded as the fundamental system parameter, system performance metric. So if we can optimize the front-end parameter, it is desirable to maximize mutual information in order to make channel better. So there are many examples. For example, MIME precoder design, semantic neural encoder, waveform shaper, shaping method, and so on. Okay, so I'd like to talk a little bit about the difficulty of the numerical estimation of the mutual information. So as you know, the mutual information includes the differential entropy HY. So for estimate differential entropy HYT, we need evaluate multidimensional integration presented in equation 5. So this part is the cause of difficulty. As you know, if the dimension is so large, taking the multidimensional integration becomes more difficult. So some people presented some mitigation method For example, by using the kernel density estimation, they presented a method for estimate the mutual information. HYT by using the KDE. So, but there is a drawback of KDE-based method. There is a strong curse of dimensionality. If the dimension is so small, it's okay, but the dimension goes large, the evaluation becomes very difficult. And also, hyperparameter tuning is very difficult. So this is a snapshot of our methods. We named the method square-to-Fisher bridge method. The first step, we use the score function estimation. I'll give you the definition, precise definition later. And then, based on the score function, we estimate Fisher information. And then we apply de Broglie identity represented in equation 7, like this. And finally, by integrating the equation 7, we get the integral representation of the mutual information like equation 8. And finally, we use the mutual information equivalence to get the final result. This is a snapshot. So I'll explain the details later. Okay, now I'd like to introduce the score function. The estimation of square function is now very hot topics in the area in the context of diffusion model, because some diffusion AI is based on the square function. So there are many methods established for learning efficiently the square function. So definition of the square function is very simple. Now U is our target random variable. U has the PDF PU. And we first take a logarithm, and then we take the gradient of U. So that's the definition of the score function. So this is just a definition. So what's the meaning? The meaning of the score function is that the score function provides vector field that points towards the direction of the steepest ascent of the log likelihood function. Maybe this figure shows the situation well. So this figure is a heat map of two-dimensional Gaussian mixture like this. This is a heat map. And you can see there are many arrows in the picture. This arrows represents the vector field given by the score function of this Gaussian mixture. So this is the meaning of the score function. Okay, now I'd like to introduce Fisher information. Fisher information, JU, is just given by this way. We can take the squared norm of the square function, and then we can take an expectation. It's just a definition of the Fisher information. This equation, this value, this is a scalar value that represents the curvature or geometric characteristic of the likelihood function. This is because if the JU is so large, the log likelihood function is steep in many places like this. And if the JU is so small, the log likelihood function is very flat like this. So this quantity, scalar value, expresses the character, geometric character of the PDF. And in 1959, very old, Stam proved the following identity. It is called de Broglie identity. This de Broglie identity connects the differential entropy and Fisher information like this. This is a kind of differential equation on the differential entropy. The proof of this theorem is based on the heat equation, heat diffusion equation, and the Fisher information. So if you have interest in this equation, maybe you can find the proof in the later part of the Cover-Thomas' book. So maybe it is better to see the concrete example. The left top is the original PDF like this. and we apply heat diffusion process onto the original PDF, we can get more smoother PDF like right top and left bottom and right bottom. So just a moment. No, okay. So in this case, the left top is the original, and so by applying the Gaussian smoothing, we get this. In this case, entropy is 1.68. This entropy is 2.60, 2.06. This guy had the entropy 2.17, and this one has the entropy 2.25. So the diffusion process goes, the entropy included. On the other hand, if we look at the Fisher information, this first one have the 7.42, and the next one is 0.5, next one is 0.15, next one is 0.05. So the Stam's theorem, de Broglie inequality, captures this diffusion process in terms of differential entropy and Fisher information. Okay, now I'd like to move to mutual information. As you know, the mutual information is just the difference between the HYT and HZT. So HZT has the concise form like this, and we can apply the de Broglie inequality, de Broglie equality. We can get the equation 14 immediately. So this is the differential equation on the mutual information. Okay. So now I move another important topic, IMMSE relationship proved by Gould, Shamai, Berdoux in 2005. It is very famous result. They used another representation of channel, this kind of channel definition. So you can see there is a parameter gamma. Gamma represents the SNR of this AWGN channel. They proved equation 16. So they connect the mutual information and the MMSE of the system. Very famous one. So, but our case, we use another formulation. So we need a variable transformation, gamma equal to 1 over t. So by changing the variable, we immediately have the equivalent identity in equation 17. Okay. So connecting de Broglie inequality in 19 and also IMMSE relationship, we immediately have this theorem. This theorem connects the relationship MMSE and Fisher information. Okay, so now I'd like to show you the Fisher integral representation of mutual information. So now we are considering the y equal x plus zt. So no front-end function. So this is just a pure AWGN channel. In that case, we already have the derivative of the mutual information with respect to parameter t. So by integrating that derivative, we immediately get the equation 21. This is an integral representation of the mutual information. So let's look at the integrand in this representation. So we can see n divided t minus jyt is integrand. And in the previous result, in the result shown in the previous page, we can rewrite the integrand into the form MMSE divided by 2 squared like this. So we now we can see the integrand decays as order of 1 over t squared. So this integral is integrable. So we can have the converged value of the integration. Okay. So finally, I'd like to we consider target channel y equal fx plus z. This is our target. So in order to apply the previous result for this target channel, we need one more key equation. So this is the theorem. The theorem states that ixyt equals iwyt. This theorem is it can be derived just by applying the chain rule to the ixyt like this, and applying some conditional independence condition, we can get this equality. Okay, now let's look at the snapshot again, roadmap. So first we estimate S, and then we can estimate JYT, and then we can integrate the resulting value. We can get the mutual information. And finally, we use the mutual information equivalence to get the final result. Okay, so, but there is a very big problem. How can we estimate the score function? So here we rely on the standard methodology of the score-based model in the diffusion model. So first, we use the neural network S theta to approximate the score function, and use the Fisher divergence for the score matching learning. So idea is very simple. So equation 29 represents the Fisher divergence. It is a kind of loss function for neural training. But you see, this loss function includes the true score function. So it cannot be accessible beforehand. So no one knows true score function. So we cannot use the Fisher divergence as a loss function for score matching learning at a glance. But fortunately, Vincent presented a very nice result in 2011. Vincent proved that the right-hand side is the Fisher divergence, and Fisher divergence plus constant equal to more tractable loss function. So we can use the left-hand side of the loss function for score matching learning. So this method is called the denoising score matching method. Okay, if we get the precise estimate of the score function, the estimation of the J is straightforward because we can use the Monte Carlo estimator for approximating the Fisher information like this. So now let's look at the numerical example to confirm the validity of the method. So first of all, I'd like to show you the case where we know the analytical solution. We consider the Gaussian channel. X is assumed to be a Gaussian input. Dimension is 4 or 8 or 16. In that case, as you know, the mutual information is given in a very simple form, Shannon's formula, in equation 34. And J and MMSE are also given in the closed form like this. And in this experiment, we use the square network, very small one, 3 hidden layer, 128 unit, and this activation. And we use the denoising score matching for computation. So this figure shows the J, estimate of J. So horizontal axis represents the noise variance, and the vertical axis represents the Fisher information. There are 3 curves, blue, red, green. This corresponds to the length 4, 8, 16. So these, from this curve, we cannot see the visible differences. There are, of course, theoretical value and estimated value. So in this case, we can have the good match between the theoretical value and the estimated value. This is the estimation results of the mutual information of the AWGN channel. In this case, we compare the theoretical value and also estimated value. In that case, as well, we have a good match between two of them. So now we change the input distribution. Now we change the input distribution to BPSK. So setting is BPSK. So minus root P plus root P are equiprobable. So in that case, of course, we have the less smaller value of mutual information compared with the Gaussian input case. In this case, we see the green curve represents the theoretical value obtained by one-dimensional numerical integration. So red curve is the square-based estimate. So there is a little bit difference, but it works well. Okay, so now let's move to more complex case. This model is similar to MIMO communication, y equal to ax plus zt. This is also linear function, so there are no non-linearity, but the benefit is that we have the analytical solution in that case. So compared with the theoretical value and estimated value, we have a good match. So last one is the final one. This is a nonlinear channel. So the channel is like this, yt equals hyperbolic tangent of ax plus zt. So in that case, we have no theoretical analytical formula for representing the mutual information in this case. So we cannot draw the theoretical value as the baseline. So this case, we use the 8 dimension. So in this case, dimension is so low, we can use KDE-based method for evaluating the mutual information as well. So we compare the two methods. One method is a conventional KDE-based estimation method, and one more result is the DSM-based our estimation. So in this case, we get a good match between two of them. Okay, so finally, I'd like to mention that limitation of our work. So this is not silver bullet. So this is not the universal solution, unfortunately. So in this case, the difficulty to estimate the multidimensional integration is somehow transferred to the difficulty to estimate the square function. So in this method, we don't need a multidimensional integration. So no difficulty in integration, but there is the difficulty to learn the square function. So for example, neural square network architecture and step depends on the problem, and number of required data samples are dependent on the problem. But I'm okay. But I'm optimistic that because we are now using the very complex diffusion model in diffusion AI, so maybe a complex PDF can be approximated with the appropriate neural network. Okay, I'd like to wrap up my talk. So we proposed a new method based on the Square-Fisher bridge for mutual information estimation. So there are several good features. Theoretically sound framework it has, and it is practical and efficient. And as far as I confirmed, it's reliable. And also, there are some significance. Maybe that kind of method can be used to design the communication system for the realistic nonlinear channel. Maybe I hope that it provides a new tool for communication system design. Okay, thank you for your attention.
Thank you for your talk. So now we are open to questions. Yeah.
Thank you very much for the very interesting talk. I would like to ask for the intuition of
Yeah.
this complexity reduction of transforming the calculation of mutual information in the definition from definition to the estimation domain. Why? What is the intuition?
Yeah, actually, consider the following situation that if the original PDF is so complex like this, intuitively it might be very difficult to learn because we need much samples for capture the figure of the PDF. So in that part, we transferred the difficulty of the multi-dimensional integration into the sampling of the PDF. So maybe for capturing the very, very complex PDF, we need many samples. It maybe cause the time increases for training.
Okay, thank you. Because my understanding is that maybe in estimation problem, the resolution of those samples, we don't need so accurate, for example. But if we derive mutual information by distribution directly through the samples, we need to have a very fine resolution to have the same precision. I'm not sure whether this is correct or
maybe I guess correct, but actually, as a matter of fact, I also don't understand fully, deeply on that point. So at the current state, I agree with your opinion.
Yeah, okay, thank you very much. Because I think the complexity reduction level is really amazing. So
yeah.
Thank you.
We have more questions.
Thank you for your talk.
Yes.
I also want to talk about the complexity.
Yes.
So you said that it can become hard to estimate, and the neural network needs to be scaled accordingly.
Yes.
So did you in practice find like a bound where you couldn't increase the dimension anymore?
Yeah, that's not currently we did on this line. So that's I really agree with your thought, but I have no correct concrete answer to your question currently.
Okay. Next question to that is there are also universal mutual information estimators, also based on neural networks. Did you consider comparing these in your work with this method?
We compared, for example, the conventional KDE and ours for high dimension. Our method beat the conventional one. Okay. So maybe this method is more robust for the increasing in the dimension.
Okay, thank you.
Do we have more questions? No. If not, let's thank the speaker again.